We've been talking about radioactive decay and question, why do nuclei decay? And then a better question is, why do nuclei stay together at all? Because if you think about it, what's in the nucleus? Well, the nucleus contains protons. All those protons are positively charged. And they should repel each other. Making the nucleus fly apart. So science started to realize that there must be something in the nucleus that's overcoming the electrical force. The electrical repulsion between the protons. So they decided to call it the strong force. Okay? And what we know about the strong force is that it is stronger than the electric force. We're going to write electromagnetic force. Because as we're going to find out in our magnetism unit, electricity and magnetism are tied together. But the other thing about it is very short range. It exists only inside the nucleus. If you remember, the force of gravity and electromagnetic force, they extend to infinity, but the strong force is only over a very, very short range. So science has now come up with this idea that there are only 4 fundamental forces, and they make up all of the other forces that we see. For instance, the normal force between my hand and a desk, if I push down on the desk, is actually the electrical repulsion of the molecules in the desk to the molecules in my hand. So our 4 fundamental forces are gravity, and the electromagnetic force, which we're pretty familiar with. The strong force, which holds nucleuses together. And then there's another one called the weak force, which also exists inside the nucleus and plays a role in radioactive decay. But we don't really need to know much about it. So there's a table here of the 4 forces, and it lists them in order of strength. Or gravity is the weakest of the forces. It's actually weaker than the weak force. The electromagnetic force is strong, and the strong force is stronger yet. The extent, gravity and electromagnetic force are infinite. Strong and the weak force are very short. This number right here, the 10 to the minus 15th, that imposes a maximum size on nucleuses. If you think about it, there's only about 100 different types of atoms, different types of nucleuses. The biggest have atomic numbers around 100. If you try to build bigger ones, you go beyond this length, this distance, so the strong force can't hold it together anymore, and then the electromagnetic force causes the protons to repel. Gravity is really important. It's very, very weak, but everything feels it, everything with mass. So it does things like pulls stars together, pulls planets together. So it's a very important force, even though it's weak, because everything feels it. Next thing we're going to study is half-life. You should be familiar with this from earth science and from chemistry. Half-life is the time for half of a radioactive sample. To decay. Radioactivity is kind of a funny thing in that you can't look at any single atom and know when that atom is going to decay. It might decay in the next second. It might take a million years. But if we look at a large sample of a radioactive substance, we know about how long it will take for half of it to decay. So here's an example problem. Substance A decays into substance B with a half-life of 2 days. We'll start with 100 grams of A. How much of A and how much of B will I have left after 6 days? So the problem is going to look something like this. We're going to start with 100 grams. And then after one half-life, which is 2 days, we're going to have half of it left, so 50 grams. And then another half-life goes by, another 2 days. Then we'll be left with 25 grams. Half-life, another 2 days. And we'll be left with 12.5. And up here it says I only have to go for 6 days, so I've gone 2, 4, 6 days. I've completed the problem. So the answer is there is going to be 12.5 grams of substance A left. It's also asking about substance B. Substance A isn't just evaporating or disappearing, it's changing into substance B, and sometimes we forget that. And if I started out with 100 grams altogether, I have 12.5 grams left of A. If I do 100 minus 12.5, that's going to give me 87.5 grams of substance B. Okay, so far we've been talking about natural radioactivity, things that naturally give off alpha particles or beta particles. We're going to start talking about artificial transmutation. And this is when you hit a nucleus that wouldn't decay on its own with a particle. It could be an alpha particle or a neutron or another nucleus, and cause it to decay. So we have a problem here. Uranium, and this is a typo, this should be 235. So let's change that to 235. Uranium-235 is bombarded with neutrons, causing it to split into barium-141, krypton-92, and some neutrons. And we're going to see how many neutrons are produced in the reaction. So we're going to start out with uranium-235. And if we look up the atomic number of uranium, it's 92. We're going to hit it with a neutron. A neutron has no charge, but an atomic mass 1. It's going to produce barium 141 krypton 92, and maybe something else. So we have to look up the numbers for barium and krypton. Barium is 56, and krypton is 36. And then we have to make the top and the bottom balance. So on the top over here, I have 236. And on the top on this side, I have 141 plus 92. And if I add those together, I'm going to get 233, which gives me a difference of 3. So I'm going to do this up here is going to have to be a 3. On the bottom, I have 92, and if I add 56 and 36, that also gives me 92, so I don't need anything here. So if I take a look at this, I have to figure out what it is. Well, it has no charge and a mass of 3, so that could be 3 neutrons. So X equals 3 neutrons. And we're going to finish off talking about nuclear fission and nuclear fusion. Nuclear fission is when big nuclei split into smaller nuclei. So the example up above would be one of those. Uranium-235 splits up into something with a mass of 141 and 92. Those are smaller, so that is nuclear fission. And when this happens, energy is released in the process. We use this in atomic bombs and in nuclear reactors. Nuclear reactors are controlled nuclear fission, and atomic bombs, nuclear fission, allowed to get out of control. Nuclear fusion is small nuclei combining to form larger nuclei. Okay, and that, for instance, down here we have hydrogen combining with another hydrogen, making helium, which is a little bit bigger, releasing a neutron in the process. That's an example of a fusion reaction. And you also get energy out of these reactions, and we use those to make hydrogen bombs, and it is also the reaction that is powering the sun.